Hello and welcome to this edition of 30 Mechanical Minutes, virtual content for real-time professionals. My name is Doug Picklyk. I'm the editor of HPAC magazine, and we're premiering this episode of 30 Mechanical Minutes at the Modern Hydronics Summit 2021. Our topic today is air-to-water heat pumps, and I'm joined by a regular contributor to HPAC magazine, Mike Miller, Vice President of Sales with Takeo Canada, and Mark Strangways, owner of the Hydronics team, a design-build mechanical firm in Toronto. Hello, gentlemen, and welcome.
Hello, Doug.
Hey, Doug.
Hey. So first, I'd like to acknowledge our sponsor for this session, Arctic Heat Pumps. Thank you for your support. Mike and Mark, we're here to talk about this emerging market of air-to-water heat pumps, something you both have experience with. Mike, how about we start with you? Can you just tell us a few reasons why there's so much talk about this technology right now?
Yeah, great question, Doug. So we see several regional jurisdictions are trying to drive us away from fossil fuel type heating systems or sources. With the increase of carbon taxes and so on and so forth, that we'll probably see that accelerated a little bit. And also watching other markets like Europe as an example, you see a heavy adoption of this type of technology, where in the last 5 or 6 years already, we see heat pump technology outselling fossil fuel fired equipment. So we certainly expect that trend to continue in our marketplace as well.
Okay. So, Mike, we've all heard about heat pumps, I think, but then we've also heard that when it comes to colder temperatures in Canada, below -15, -20, we've heard that heat pumps can have their limits. So, can you kind of help us understand why this technology is so efficient?
Yeah, that's a great question, Doug. Thank you. So I got a couple of slides that talk to the heat output or cooling output limitations related to ambient temperatures. So I just want to share that with you. I hope you can see the slide. And this is just a particular example. There's different manufacturers, different equipment out there that has different type of temperature ranges, but in general, what you will often find is that the fluid temperature that you can get out of a heat pump is generally limited to 140 or below in Fahrenheit. And you'll also see some limitation where this temperature begins to fall off as the outdoor air temperature gets colder. So in this example here, you'll see that this particular heat pump could produce with a R410 refrigerant a steady flow temperature of 60 degrees C or 140 degrees Fahrenheit to about -5 degrees C outside. But as it gets colder outside, you'll see the heat output or the water temperature that it can produce to fall off a little bit, down to about -22 degrees. Many heat pumps can still produce 110 or greater water temperature or 45 degrees C. But right here, I want to point out that there is a time at which, when it gets cold enough outside, you might be looking at some auxiliary heat to supplement that. Then also, still in the same manner, here's an example of perhaps a 12 or 13-ton heat pump. You see that as the outdoor air temperature gets colder, its output capacity drops down a little bit. So I've added some BTU numbers here as an example. And this is just one example. But in general, this equipment is similar. As it gets colder outside, you'll see the output reduce a little bit. Again, highlighting the need for some auxiliary heat when it gets really cold outside. But I want to highlight that there's a lot of the time throughout the year where the heat pump alone can produce enough heating and cooling. What you'll see on the right-hand side here is the coefficient of performance. You'll see that heat pumps can operate in quite a high COP throughout the majority of the year. And again, as it gets colder outside, the efficiency will drop off. In cooling mode, generally, there's also operating limits, but most heat pumps can produce up to about 40, 45 degrees Celsius outside or 110 degrees Fahrenheit outside, which is quite nice, certainly not in my area. but it can produce a temperature anywhere within that range, which could be as low as 7°C or 45 degrees Fahrenheit, which is the kind of fluid temperature you would need if you're dealing with like a fan car, as an example. Same thing there. Your cooling output begins to fall off a little bit as it gets warmer outside. So while you might have a larger piece of equipment, you have to be able to still provide enough cooling when it gets warmer outside during your design point. So always be mindful of that unit's output capacity based on outdoor temperature. Thank you, Doug.
Okay. Now, Mark, we come to you. I know you've had a hand in installing hundreds, if not thousands, of water-based hydronic heating systems. So let's start with what's the biggest difference from a design installation standpoint that contractors need to understand with an air-to-water system?
Okay, well, when designing the system, you have to take into account the lower water temperatures available or that are being produced by the equipment. So if you're using forced air, you'd have to ensure that the A coil or slab coil that's going to be used to exchange the heat has large enough surface area that it can produce enough BTU for the home, given that water temperature, given the airflow that's passed across it. If you're using something more like radiant inflow, it's already sized to utilize lower water temperature, and you can generally make better use of your lower water temperature that heat pump's able to or limited to produce.
Right.
With a cooling, same with cooling. Cooling using forced air, coil selection is equally important to ensure that you're able to remove the latent heat and the sensible heat from the home. Otherwise, you're going to be having some problems with your wife.
I think you had mentioned earlier too that maybe in a retrofit situation, if you were using a forced air, for example, ducting may be an issue as well.
Yeah, depending on what's coming out. In the past with ground source equipment, if we're retrofitting it into an installation where there might have been a forced air, oil-fired forced air furnace, due to the higher air source temperatures of forced air, of the oil-fired forced air equipment, less airflow is delivered. When you start reducing the air temperature available, in order to move the same amount of BTU, you have to increase the airflow. That can put a strain on ducts that may not have been sized, for today's standards. Today's standards generally have larger ductwork, larger distribution networks than they would have had in the 70s or 60s. Right.
And again, in a retrofit situation, you're dealing with a lower water temp. So if it's not and if you're moving into an existing hydronic situation, if it's not in floor heating, what does that bring about? Like you're adding heat emitters, I guess. Is that?
Sorry, I missed the question.
Oh, sorry. Just a retrofit into an existing house with a hydronic heating system. Because you're going to the lower water temperature. Yeah.
Well, a few ways you could handle that. Yeah, you would have to add some surface area to your heating system, be it radiant floor if that's possible, maybe radiant walls. Change out the rads to bigger units that are sized to operate at 120 or 110 degree water temperature. Many different ways you could do it. Sometimes the easiest way is just to let the heat pump provide a large portion of the heating up until it's limited its water temperature, and then take over with an electric boiler or, dare we say, some fossil fuel appliances, but just to supplement in those days that, they're not especially in urban areas, there are not a lot of days where we're in design territory. And for a large portion, even the old cast iron rads could, quite satisfy a house at 120-degree water temperature.
Okay.
Yeah, radiant floor heating is often already designed with the low fluid temperature, so that would make it a perfect match for a heat pump application. But like Mark was saying, if you got panel radiators or whatnot, you may have to increase the surface area of those. But there's also some very modern, up-and-coming types of thermal units out there now that become more effective with the lower temperatures. Like an example I can have is, there's some radiators available that are now fan assisted, that now give you the benefit of having some radiation, but then also some fan induced heat output, which allows you to still produce a fair bit of heat output at the lower fluid temperatures you deliver to it.
Okay. And I think you're also talking domestic hot water solution using the air to water heat pump. Did we?
That's a great question. So heat pumps can also we can also utilize the fluid to produce domestic hot water. It's very important to be mindful that when you size or pick your indirect domestic hot water tank in this case, that it is slightly different from a traditional indirect by it having a much larger surface area available. Because you have lower water temperature available, you need a greater surface area in order to emit the heat to the potable water. So there is high output types of indirect tanks that give you that larger surface area. Here's an example that I got on the screen. There's one that uses between 2.7 and 3.5 square meters of or 35 square feet of surface area to allow hot water production to 115 or 120 degrees Fahrenheit by only sending 140 degrees or just below that to the coil. So it still provides enough hot water and warm enough with the larger surface area that you provide in the coil.
Okay. Now, Mark, I understand I know you installed a unit in Mike's house. And Mike, I understand you're using an air handler, correct? For heating and cooling?
Great question, Doug. Thank you. So actually, I got a house just like most folks might have, where the existing system looked kind of like this, where we just had a 2-stage gas furnace that did the whole heating in the house. So it was already ducted for it. And there was a DX coil that would provide the cooling. And for my hot water use from the rental company, I had a high efficient instantaneous water heater, if you so will. So that would do my domestic hot water, and this furnace would do my whole heating and cooling. Now, Mark was kind enough to help me convert that into a hydronic heat pump system. So to answer your question, yes, I could have replaced it with the fan coil, but what we chose to do in my house is we left the furnace in place and modified it slightly. So we removed the AC coil or the DX coil that was in there previously, and we sized an A coil that we put in its place, and the A coil became the hydronic coil. So now we send heated water through it in the heating season and cooled water through it in the summer during cooling season. And we still utilize the fan in the furnace and the existing ductwork as our distribution system.
So Mark, what were some of the challenges of putting this system together?
Well, with any retrofit, it's obviously getting pipe work through an existing house, especially finished basement, as in Mike's case. One thing people have to keep in mind with a system like this, we're dealing with chilled water. All pipes have to be insulated. Otherwise, you're going to have some condensation problems in the ceiling. Space constraint, if you have a small mechanical room, trying to get, a larger domestic hot water tank and a little buffer tank or a larger buffer tank, depending on the size, can be problematic, but you know, we solve these problems.
And yeah, so can we talk about that? I see we've got the buffer tank involved here, and that's a necessity when we're dealing with air-to-water heat pumps.
So,
Right.
yeah, so the buffer tank in this case here, as you see, oops, there we go. Yeah, so the buffer tank's purpose here is when you run a heat pump, you want to minimize it from short cycling, which in an air-only system, like in this example, not the biggest deal, but if you're talking about radiant floor heating as a heat emitter, you may have times where only a small portion of the system is physically calling for heat. So the buffer tank then gives it enough mass so that when the heat pump does turn on, that it doesn't short cycle. So following some of the examples that the Europeans are using, when they turn on a heat pump, they want to make sure that they don't turn it on more often than 3 times an hour. So often this buffer tank is sized in order to give you the 3 cycles per hour, potentially. So the added mass to give it the longer run times. But then there's also, in many cases, different technology inside the heat pumps, whether that is staging through different compressor stages, or in other examples where the heat pumps are now inverter driven, which allows it to modulate the compressor through the power supply. Yeah, Mark, do you have anything to add to that?
Not really. Just hit on what you said. It's just as with any real appliance, you want to keep it running as long as possible and keep it off as long as possible, and the buffer tank certainly helps that. In your drawing, you show an electric backup heater in that tank. You know, in your situation, you elected to use the electric boiler. So we're using that electric boiler to supplement the heating should the outdoor temperature fall below where your heat requirements are in the house. It also supplements the indirect, and I know you're using it to bring your tank up to 140 or so once a day to kill off Legionella that might have developed in the tank from a lower operating temperature. That, as you show in your buffer tank, that could be accomplished with independent electric heaters in each of the buffer tank and the indirect. But the better approach, I think, is just one electric appliance that could be modulating or staged, that is a as needed type of device more than a it's on until you don't need it anymore, as with immersion heaters are.
Yeah, that's a very good point. Now, perhaps maybe let's talk about this piping arrangement a little bit, because it's probably a little bit different than what most folks are familiar with. In fact, this is a concept we've seen over in Europe, where they utilize a number of check valves and a different type of piping arrangement in order to physically isolate one loop from another. So I just want to cover that quickly. Here's an example of a heat pump where the supply comes down. There's a couple of T's that have a valve in there that is typically, it's always closed off in my case. So we're sending the water through this electric boiler. It's a nice 2-stage electric boiler. I got this one from a good friend of mine. So it flows through the electric boiler. And for heating purposes, these check valves are pointing down, so the water could physically only go down into the buffer tank, back out of the buffer tank, and then back into the heat pump. So that's the heat pump circuit for heating and for cooling for itself. Now, when that heat pump operates for domestic hot water, it would go from the supply through the electric boiler, through this pump, which now services the indirect coil in the domestic hot water tank, and then it returns back to the heat pump. So here's your heating and your cooling pump from the heat pump. Here's your indirect domestic hot water pump. And then this pump would go to your heating system, whether that's radiant floor or, in my example, to a coil in the furnace or a fan coil. It would then only run the water from the buffer tank, heated or cooled, depending on the season, through that coil, and then back through this check valve points up, so it can't go down this way, so there's no way to short circuit. It would come down this way and then return back into the tank. So with both of these running together, they would be hydraulically isolated by basically working with each other, not against another. The other thing that we wanted to point out, Mark, I think we had some electrical limitation to being an older house, being retrofit. I only had 110 amp or 100 amp panel in my house, so we had to go to this example. Because what did you tell me? I think if we had to put elements in each of these tanks, what would that have meant?
Yeah, if you're supplemental, you have a 6 kilowatt boiler, so that's calculated based on what your supplemental needs would be for heating. You'd have to have a 6 kilowatt in that backup, or a 6 kilowatt backup heater in that buffer tank. Then you'd also have to have another, depending on the size you want, the length of time you wanted to take to heat up that domestic tank would kind of dictate what size of element you wanted to put in there. But each time you add that 240 volt high power element, it's another 30, 40, or 60 amp breaker in the panel, and that can lead to some problems where if you don't have a 200 amp service in your house.
Yeah, very good. So yeah, that was so the heat pump itself in my house. I think that is on a 40 amp breaker. You put it on, and then we have another 40 amp breaker for that electric backup boiler. And had those been elements, those would have been two 40 amp breakers. So that would have been exceeding my power supply. So unless I would have gone through additional electrical expense, this was the most cost-effective solution that I believe is also the best way to keep that in check.
It certainly allows the system to respond to what is actually needed, not just dump 6 kilowatts in at a time.
Right.
Mike, can you address why the tankless water heater remains? Why do we need that there?
We left it there at the beginning because, again, like Mark alluded to earlier, the happy wife, happy life. We left it in there at the beginning, basically just as a backup in case we weren't getting enough heat. I never had any doubt, but the wife wanted to make sure we were good to go. So instead of arguing with her, I kept some peace of mind. We basically ran the cold water into this tank, into this indirect tank first, where of course the heat pump with, when needed during cold outdoor temperature, the electric boiler would assist it. It would always satisfy all of our hot water needs. So basically, we took the hot water discharge from there instead of going straight through to the building and then into the actual bathtub or sink. We ran it through the tankless coil anyway, so the tankless instantaneous heater, to provide any boosting if it was required. That unit hasn't run since we commissioned this system. So I'm trying to fight with the local utility company to come pick it up because I don't want to pay rent anymore. I don't need it anymore. So yeah, good question. So thank you, Doug. Okay,
Mark, I'm curious about we talked about what these air to water heat pumps can do. If you needed to satisfy a larger space, can you cascade these systems? And then what about things like zoning, those sorts of things? What makes these different?
Cascading is certainly possible. It's internal cascading would be on a manufacturer by manufacturer basis, but there's a lot of third-party controls out there that can look after cascading 1, 2, 8, 10, whatever units, whatever your capacities are required. You could certainly stage multiple heat pumps the same way you'd stage multiple boilers.
Right. Okay. And Mike, maybe you can talk to us about the efficiencies versus upfront costs when it comes to these air-to-water heat pump systems. I know these systems are making sense, but how do they always come down to dollars and cents, perhaps, for homeowners? So how do we justify these costs?
Again, another good question. So heat pump technology, whether it's a ground source or air source, first and foremost, is not necessarily cheap. They do have a cost associated to them. However, when you see things like carbon taxes being added by the government, you know, and there is already, we know coming down the road, those are going up significantly. That will accelerate the payback of such a system already just strictly through that. But then also there's several provinces and maybe even local jurisdictions that offer great incentives or rebates for equipment such as this, where often that could cover as much as 30, 40, 50% of the upfront cost. In terms of operation, I can tell you that at my house, it's completely removed the use of gas. Like I no longer have the gas burning for the tankless unit or even the furnace itself. It's added about $80 to my electrical bill on average. So it's a very cost-effective solution. In fact, I'm actually making money if I'm not paying the rent for this equipment, and I'm looking at all the rebates that are available these days. The ROI is getting a lot shorter.
Very good. I'm curious from both of you if, I mean, from what you've experienced with installations of these things, what maybe has surprised you the most? Or maybe what you didn't expect when it came to one of these systems? Mark, do you want to go first on that?
I don't know. I guess I've come to expect the unexpected. With hydronics, every job's a new job. Every job's different, and we roll pretty well with that. We've done an awful lot of ground source work, water to water, water to air. I don't think I really found anything that I needed to get my head around to, you know, fix or to get my head around to understand why we had to do it a certain way. I think as somebody who's going to install one of these first time, definitely understand that there's chilled water involved and you have to insulate everything.
Right.
Understand the basis of low water temperature equipment requires quite often a higher flow rate. So, you know, make sure pipe sizes are adequate to handle the higher water flow rates, generally around 10-degree delta T between, you know, the inlet and outlet of the heat pump, or, you know, the inlet and the outlet of an A coil or a slab coil. With in-floor or steel panel rads, cast iron rads, there's a little bit more flexibility to the distribution end of it, and where you might have a, you know, mechanical panel might be a little bit more simplified because of that. But you know, in this case, it's fairly straightforward enough, at least in my mind. Just keep in mind that, you know, insulate and seal pipe work so we don't have any air touching cold surfaces that could condense, and make sure you've got large enough pipe diameters to handle the intended flow.
Awesome. That's awesome. Mike, any final comments on your experiences with air to water heat pumps?
Well, I'm absolutely floored and thrilled by the technology. I love it. Got a lot of passion for it. I can tell you from my own house, just coming from a furnace that used to scorch the air in the winter to provide heating, and completely chill the air in the summer for cooling. I noticed a bit of a difference where before, when I felt hot air coming out of the air vents, it is now tempered air for both heating and for cooling. It's not as cold, but it's more consistent. So I find That of course the fan runs a little bit longer, as Mark alluded to earlier, with the lower fluid temperature. There's something needs to give. You get less lift of the air temperature as it goes across the coil, so it runs a little bit longer. But I found that it added a lot of balance, and it also reduced my need to humidify a lot in the wintertime, because it didn't pull all that air out through the flames. Yeah, it increased the comfort level, I would say, Doug. Absolutely.
That's great. That's great. You know what? I think we're out of time, so I want to thank both Mike and Mark for sharing your experiences with air-to-water heat pumps, and thank you to everyone who's been watching. Now,
Thank
for
you for
those
the
of you,
opportunity.
yeah, thanks, guys.
Thank you.